morning. In the last class, we have learned about the torque. What is a torque? Today we can prove the Kepler second law of planetary motion, and it is we can use the angular momentum concept, and the rate of change of angular momentum is zero. That is the conservation of angular momentum concept here. That is, there is no torque here. So that is we can do, or we can derive, or we can see that the second law of Kepler's second law of planetary motion can be proved of using the using the concept of the conservation of angular momentum. For that we are using a central force. This is actually a central force problem, and a central force problem and the law of equal areas. So all planets are moving under a central force, and we can go into the central force motion and the law of equal areas. Central force motion and the law of equal areas. So what is a central force? You will learn about the central force in next semester in detail in the next semester. I think in the third semester you can have the central force problems. But I can just give the definition, or I can just give what is a central force. A central force is the force that acting along a line which connects the object and the origin. It is a force that directed along the line joining the object and the origin. That means origin to the object means, that means if you have some object here, so this is the line joining the origin and the object. This is actually the position vector of r with respect to the origin. Then if the force is acting along the same line, then that is a central force. That is, it is a force that directed along the line joining the object and the origin. That is known as the central force. So the force is also acting along the same direction. That is known as the central force. So we are now dealing with such type of force, that is the central force. So planetary motions are actually central force, actually having central force, or it is moving in the central force. That in 1609, Kepler announced the law of planetary, his second law of planetary motion. Kepler announced his second law of planetary motion. That is, this is the law of equal areas. The law of equal areas. So what is the law of equal areas? That is, it is actually known as the area swept by a radius vector from the sun to a planet in the given time is, say, for any location of the planet in its orbit. The area that swept by the radius vector from the sun to the planet in a given time is the same for any location of the planet in its orbit. That means the area swept by the radius vector from the sun to the planet at any location in a given time is a constant. So that is why we can see that how the planets are moving around the sun. The planets are orbiting around the sun in an elliptical orbit with the sun at one of its foci. is the, you can see that the planet, this is the planet here at some time, and after delta t time the planet reaches at this point. So this is for at a delta t time. So the area swept by the radius vector in the given time delta t is, we can see that this is the total area covered by this planet in a delta t time. So according to the law of equal areas, if we are taking if the planet is at some position here at a given time, then after a delta t time, the area swept by the radius vector here should be also the same. So you can see that at a particular time the planet is here, then after delta t time it should reach in a position such that this area should be equal to this area. So this is the area here and this is the area here, and in a given delta t time this area and this area should be a constant. That is the law of equal areas given by Kepler. So you can see that. So how we have to get the same area here? So if the planet is moving the same velocity, if the planet is moving at a particular velocity v here, if the planet is moving in the same velocity here, we will not get, it may reach some here after delta t time. So, but you can see that this is, we have the law of equal areas, so the planet should reach here in a delta t time. So what we have to, what the planet is doing, what is actually happening, what is the thing actually happening there? Here, near to the sun, the planet will move faster than when it is far away from the sun. Here the planet is moving faster than the velocity when it is far away from the sun. So here the velocity will be less compared to the velocity, so that it can cover equal areas in the given delta t time. So this is actually sun. This is the one of the foci of this, what is this, elliptical orbit. So you can see that this is actually the thing happening. This is the law of equal areas. So this is at B, position B, so this is at A. So the shorter radius vector B is compensated by greater speed at B. So at these positions, the planet will have more velocity than the planet at A. And the law of equal areas directly follows the considerations of the angular momentum, and it holds for any motion under central force. The law of equal areas directly follows the consideration of the angular momentum, and it is valid for any motion under central force. So we can prove the central force, this law of equal areas here. For that, consider this is a point, this is the origin or whatever, this is maybe sun. So we can draw a line here, this is the radius vector r here. So the planet or the object is moving to some other position. So we can draw the radius vector from here to here. This is the origin O and this radius vector is r. So this is at a given time, the position of the r is here. So the position of r at some t plus delta t is this one. This is the position of the object or the position vector of object in a time r of t into t plus delta t. So consider a particle which is moving under a central force. The central force some Fr. So this Fr can be written as F of r into r cap, since the central force is directed along the line joining the origin and the object. So this is actually Fr of r cap, unit vector is along the direction r. So what is the torque acting on the particle above the origin? The torque tau is given by r cross F. Here r cross F r cap. But you can see that this r and r cap, or this r and the radius vector or the position vector or the radius vector, and the force is acting along the same line. So the cross product will be 0. That is tau is 0. That means if tau is 0, tau you can see that what is the torque? The torque is actually dl by dt, the rate of change of angular momentum, which is if this is equal to 0 implies L is conserved, or L is a constant. So you can see that the central force, in a central force motion, the torque is 0, so that the angular momentum is conserved always. So the angular momentum is constant both in magnitude and its direction. So the motion is always in a